Assalamu alaikum students, welcome to lecture number 16 of week 8. So we are moving towards the end of our lectures and after this 2 lectures are remaining. So this is a very interesting lecture. In the previous lecture we have learned about the surface spin glass behavior in megamite nanoparticles, in which the spin glass peak was not very well separated from the blocking peak. We have a overlap of both peaks, but still we were able to identify the presence of spin glass behavior by some indirect measurements and models and calculations. So here we have a very interesting system in which we have a separate spin glass peak and a blocking peak, which is the nickel ferrite. Here is the preparation for the spin glass peak, and you can see this is the phase diagram of the nickel ferrite nanoparticle, which shows that there are different phases present at different annealing temperatures. So at 900 degrees centigrade of annealing, when we prepare the nanoparticles, we get the single phase nanoparticles, and below 900 we have a different kinds of phases as present. So why I am present this phase diagram, the reason is that because when you are doing some research, you should first prepare the nanoparticle of single phase, what you want. In this case I need nickel Fe2O4. If I anneal this sample at 600, for example, then your sample will contain nickel oxide. If you see vertically at 600, you have a nickel oxide, alpha Fe2O3, and a nickel ferrite. So and this is a problem because nickel oxide and alpha Fe2O3 is anti-ferromagnetic system, and your nickel ferrite is ferromagnetic system. So during the research of the nanomagnetic systems, you first ensure that you will get the single phase system which you want to study in detail. Otherwise you will mix your system with some other magnetic phase, and you will end up in the wrong wrong conclusions. So here is the zero field Cool curve of this single phase nickel ferrite nanoparticles of 8 nanometer taken at 200 Oersted, and you can see the zero field Cool curve is a little bit different because there is some hump below 50 Kelvin, and the blocking peak is very broad, and it was further investigated by AC susceptibility. And on the left hand panel you can see the out of phase part of the AC susceptibility, which gives a peak at the same temperature region where we got the hump in the DC measurements. So in AC measurement, especially in out of phase part, we get a peak in the low temperature region, and we have prepared different size nanoparticles, and you can see 8 nanometer particle have a very clear peak, and which vanishes with increasing the particle size. At 27 nanometer, this peak is nearly vanished, because when you're increasing the particle size, you are decreasing the surface defects, and even when you are decreasing the surface defects, you have less small surface to volume ratio, and you have a weak surface core shell interaction, and you have no spin glass behavior. So spin glass behavior is present in this scenario in 8 nanometer and 12 nanometer system, and the high temperature peak belongs to blocking peak, and the low temperature belongs to the spin glass peak. So here the next figure on the right side, the exchange bias or shift is presented in the inset of figure on the right side. You can see there is a clear shift in the 5 Tesla field cool loop, which gives information about that there is some kind of exchange bias is present in this system, which is due to the coaxial interaction. So we have taken the AC susceptibility at different frequencies, and particularly we want to study the smallest size sample, 8 nanometer. So these figures are only for the smaller peak, low temperature peak. You can clearly see this the low temperature peak shows a TG. The spin glass transition temperature shows a shift with increasing the frequency, which is due to the change in the anisotropy of the barriers of the system with frequency, and it is a hint for the presence of spin glass peak. So in the fitting, we have here shown you the scaling law of fitting, which is very famous for the to study the spin glass behavior. And Arrhenius law, of course, does not fit well to this temperature to this system. So here we after the fitting of the change in blocking temperature with frequency, we got ZV parameter, as I told you, is very important, of the equals to 705, which lies in the spin glass region 4 to 12, and the tau static is the spin flip time of the nanoparticle, which is high due to the slow relaxation, which is a typical fingerprint for the spin glass system. And T naught is the spin glass freezing temperature, which is equal to 10.8 Kelvin. So the other indirect evidence is the AC susceptibility under the applied DC field. We have taken the AC susceptibility by applying the DC field, and with the application of the DC field, you can see the blocking piece is shifted towards low temperatures, because we have force over particles which are along the field axis to remain in the field axis, and there is no jump in the other direction, and we need but for the spin glass peak, it remains unaffected, which is due to its metastable state, and we are thus two valley anisotropic barriers not valid. We have energy landscape of energy barriers. So the temperature dependent of coercivity is also presented, where you can see we have a sharp increase below 50 Kelvin, which is also due to the increase of coaxial interaction, which hinders the reversal of the core magnetization in the field direction, and we have a more coercivity or more open loop at low temperatures to the blocking of the surface. And in the right hand side, we have a thermoreminent magnetization, and you can see near the spin glass peak, and it is normally flattens if you have a spin glass, and if you have a near the blocking peak where the surface spins becomes defrozen, we have a sharp decline. So if you have a sharp decline like that, you have a hint that you are above the TG. So below 50 Kelvin, the flat the curve, the thermoreminent magnetization is flattened, and this thermoreminent magnetization is the similar like we have relaxation. The only difference here is we have plotted them on the x-axis as log of the values. Otherwise it's the similar zero field core relaxation. The memory fact is the fingerprint for the spin glass behavior, and here you can see on the left hand side figure, which is taken the difference between the reference curve and the weighting curve. So for the weighting curve, three curves, these are not the curve, these are the difference of curves. So we have one reference curve and the three weighting curves. For the first weighting curve, we cool down the sample and wait at 12 Kelvin for 2 hours, and then go to the 4 Kelvin and take the measurement. And for the next curve, red one, we have stopped at 10 Kelvin during the cooling for 2 hours, and then went to the 4 Kelvin and then take the measurement. And for the 8 Kelvin, we went cooling down at 8 Kelvin. We wait there for 2 hours, and then we go to the 4 Kelvin and we see the then we have taken the measurements. And then we have subtracted all these curves with the reference curve with no weighting AC accessibility curve, the zero field cool protocol. And you can see clearly a dips present at the waiting times, because when we have waited in zero field cooled protocol, we have increased the disorderness in the system, and this is a clear hint of presence of spin glass behavior. On the right hand side, we have shown the M versus time curve, in which we have before taking the curve at 8 Kelvin, we have waited for 0 hours. Immediately we have taken the curve, then we have taken the curve after 1 hour, then we have taken the curve, the same field cool zero field cool relaxation curve after 2 hours. You can see there is a difference. If there is no difference, then you have a no spin glass behavior. So actually the time experiments tells you about the relaxation experiment, tells you about the fingerprints of the spin glass behavior. So there is negative cycling of temperature in two protocols. The left one is the zero field cool. You have taken up to 2000 seconds, then you went to some other temperature, and then you switch off the field, and then you measure for 2000 seconds, then you apply, then you went back to 8 Kelvin and apply same field as in the previous one, 50 Oersted, and you got the same magnetization at 8 Kelvin as you have you have restored the curve. Similarly, you have restored the curve in the other figure, field cool. So, in conclusion, 8 and 12 nanometer particle dispersion silica matter exhibits spin glass freezing and blocking at low and high temperature respectively. Spin glass freezing is due to the disorder surface spin. Blocking and freezing while separated in these systems. This system shows memory aging and negative cycling, which is best proof for the spin glass behavior. Effect is not from the dipole interaction. And this is all for today's lecture. Allah Hafiz.